Welcome back to Simulation and Prototyping. While the class that I've been teaching is over, I continue to develop new aspects to the work that we've been doing with Rhino and Grasshopper. And so I'm excited to share this new project that I've been playing a little bit with. And what it does is it uses the Anemone loop to create flow lines across a surface, essentially simulating the flow of water. And I do a couple more things here that the color gradient that I've developed, and I'll explain how to do this over the course of this tutorial. The color gradient changes according to the slope, not the length of the line, which is a very easy thing to use the gradient to do. But what I'm actually doing is taking the continuous flow lines, splitting them up, analyzing the slope along that curve, and then color coding it. And so we can see, as we look at this, that where, and at least with this gradient, where the slope is relatively low, it's green, and where the slope increases, it's blue. And I'll show you how to set these things up. The other thing that I'm doing, I just wanted to add, in terms of representation, something where the flow line starts. And so what I did is I created a small circle at the beginning, and those circles are oriented according to the flow. And so you can see the way that those change across the surface. The way that I've set this up is with a random number, or a series of 3 random numbers that allow us to change the topography. And so as the topography changes, we can see it takes just a second to update. We can use a series of random numbers to generate the topography. Here, we're using a patch surface to do that. And we can see the flat, relatively flat spots along the flow are green, and greater slope is blue. And I can do one more, and what I have set are just variations of the seed value for the Z values of the patch surface. And so as this updates, we'll see another version of that. We'll build it in a couple of different ways. So here we can see another version and the way that water might move across that surface. So I think it's a really cool visualization technique to be able to understand topography. And we'll try a couple of different things or slight variations from what we're seeing right here, but I'll explain those as we go. So if that's probably a good introduction to what we're going to do. This will give you a good sense about what we'll build. And then as we go through it, I'll explain why we're doing some of the things that we're doing. So I'll start with a new Rhino file. I'm going to do large objects feet. And I'll do a new Grasshopper document as well. And I'll start by dropping in bifocals just so that you can see the name of the components that we're going to work with. So let's start. Let's see, I'll go to perspective view. We don't have anything yet. I'm going to, rather than just building a topographic surface, I want to set that up so that we can explore different surfaces. And I'll do that using random numbers. And so let's start with random. And we can actually copy this 3 times because we're going to use it for X, Y, and Z. And let's set this with a construct domain, just the simple kind of between 2 numbered domains. And we can copy this. We just need to copy it. You could copy it 3 times. if you want to have a different dimension or different orientation, what I'm going to do is use the same domain for X and Y, and then a different domain that we can control the Z. So we can use a couple of sliders here, and maybe I'll start with, probably, it looks like we're going to go, well, I'll do 0 is less than 100. And then we can copy this a few times as well. So let's set our domain between these two values. I don't really want it to be at 0, because I never really like working exactly at the origin. If something defaults to the origin, I want that to be kind of outside of the place where I'm working. Let's set this for the range for both the X and the Y. And let's set our number to be 30. So we can use the same slider, or somewhere in that range. So we can set that to be the number. And while we're at it, let's build our construct point. And we can plug these in. We don't have anything for Z yet. So as we have this, let's see, we can copy these sliders as well. For the Z, I don't want it to have quite the range. So let's set this maybe from 20 to 45, somewhere in there. We'll do that from start to end. We'll set that to be our range. And we can also set the number to be the same. And let's do, we're going to want to have different seed values for these. And what I'll do is I'll do 0 is less than, I don't know, 1000.00. And we can copy these. So that'll be our seed value. We just want to make sure that they are different, because if we have the same seed value, that can do some weird things. And for this, well, we can copy it once more. As we run this with the script and as we start doing other things, I did move away from the slider to just using a panel and feeding a very specific number to just change the Z seed value. Because if I wanted to get to something specific, and then I could replicate that. But for now, this should be okay, and we can see what we're doing. Let's take these values. And so we have a series of points we can navigate around. We can get a sense that they're within a certain XY range, and then within a Z volume. So if we find that it's too much, we can always decrease our Z. And if this gets to be close to one another, this will get relatively flat. So we'll just increase it enough so that we'll see what the range of topography looks like as we turn this into a patch surface. So that'll be our next step. And let's add that component, which is the patch. And these will be the points. And all of these are fine, but I do want to play with the flexibility. So let's set this from 0 is less than, let's say 2.00. And we'll plug this in for flexibility. And we can see when it's 0, it's It's a relatively flat, inflexible surface, but as we increase this, we don't need to increase it much. I'm going to do it around 0.6, somewhere in that range. And we can come back and we can revisit it. And you can see the more flexible it is, it will go through more of the points, but we're not trying to match all of those points. We're just trying to end up with a topography here. So if we want to check, we can manipulate our seed values and we can see the way that this will change. We can hide our points. I'm going to use Control Q as I preview and unpreview things. We'll keep our patch surface here for now. And maybe just while I'm here for a representational issue, and I am trying to focus on not only the modeling, but also some nice visualization. And so I want to do two things just really quickly. Let's create a custom preview. And let's add a swatch, color swatch. And let's grab both of these and copy them. So I'm going to do two things with this. The first is to create a custom preview of the patch surface. I'm going to make this gray, but using the alpha channel to make it pretty invisible. Just want to have a little bit, and now we can hide the patch surface itself. So now with the alpha channel and a little bit of gray, we get a sense of the surface. The other thing that I'm going to do is to deconstruct the BREP. And the reason why I want to do that is I just want to grab the edges. And so I'll set this as, or I'll use a curve container. We'll pull the edges out and we'll set this to the geometry. And we'll set those to be black. We can hide the deconstruct BREP and we can hide the curve. And we should have a nice black 0, 0, 0. Tend to use the ghosted view and not really getting the black edge that I was hoping to get there. And we can revisit this later. Okay. That's fine. Maybe this is too. Nope, has nothing to do with the alpha channel. All right, well, I'm not going to get too focused on that. We can always come back to this later. And that's good. So we have our patch surface. Now let's look at a couple of things. One of the things that I was doing previously was to make, rather than use the entire surface for the flow lines on it, I was creating a separate zone. And so what I'm going to do now is go to the top view. And this time around, I'm actually going to create a circle. And let's use a circle as a way to define our, and I'll do this with a surface and with a planar curve. And then we can move this above. We don't actually need the curve, we just need the surface. So if we go back to the perspective view, now we can see we have a round planar surface, and I'll use that to feed into a surface container. We'll right click, set one surface, select that. We can hide this in Rhino. And actually what we may want to do is to not have that hidden, but we can hide the container. And the reason for doing that is that we can manipulate this and move it around, and we'll see the way that that changes things. So in order to get a series of points for our flow lines, what I'm going to do is I'm going to divide a domain. And our domain will be our surface. Our U and V count, we can set with a slider, or in this case, I'm just going to set it with a panel. And let's set this to be something relatively low for now. We can turn this up as we go. I'm going to feed this for both the U and the V. And then the next component that we'll use is isotrim. And we'll again feed the surface into this, feed the domain into that. And interesting, I thought it would work with a circle. It seems that it's not actually working with the circle. It's just taking the domain. That's okay. Well, we want to get the area of those individual parts. Interesting. Okay, since a circle is not going to work, I'm going to delete that. And I'm going to draw a surface plane corner to corner. If I hold down Shift, it'll make it a square. And I want it to be, I don't know, maybe 1/3 to half the size. We can set that, and then we'll move it above. And then we have to feed this back into our surface container. And that's good. So this 10 value, we can see if we reduce it to 5, it's 5 by 5. I'm going to turn off my ISO curves while I'm here. So I just have a simple outline for that. And we can hide our isotrim. For now, let's keep our area there. And what's happening, if I turn this back on, we'll see that the divide domain is dividing up our surface. The isotrim then takes that and subdivides the surface. The area gives us a centroid point at each one of those. And so we could say, we could add a point container here and use centroid. As we click on it, we can see these are then those points. So let's hide, and I'm using Control Q, hiding those, and we have a series of points from above. And the reason why I wanted this was just some notion that there's some some level of control about how that surface or how the water is going to hit the surface. So we have that. Now what I'd like to do is to create a series of lines from those points that come down. And so what we'll do is we'll use line SDL, which is start, direction, and length. Our start points will be the points that we just created. The direction will be our unit Z. And because we're setting the length now, we don't have to turn that negative. We can use a negative value. And I'll just use the / minus 50, enter. And we'll see if this works. And by that, I mean, what I'm hoping happens is that it is long enough to pass through the surface. And it's not in some cases. So I'm going to change this to be minus 100. And your values will probably be a little bit different depending on where you put the surface above. But we just want to make sure that these lines pass all the way through the surface, and that even as we manipulate our topography, that these lines will pass through. And so we can leave that as it is. The next thing that we'll do is find the intersection between them. So we'll go intersection, mathematical. We're looking for B-rep and curve. And so it's under the physical. So under some of these I remember by heart and I can type them in. Other times I can't. So we're looking for the intersection of B-rep and curve. And our curve will be the lines that we've just created. And our B-rep is going to be our patch surface. So now we see that we get a series of points projected on, or the intersection between these vertical lines and our topography. So we can hide our curves, we can even hide our points above. And now we have those points on the surface. So now we're getting to the place where we want to use the loop. And we're going to use the loop to set this up to move in a certain way. And so I'll go to the Anemone, and we can do one of two things. And given the number of points I was using and the way that I'm subdividing them later, I'm using the fast loop, but we can actually, it's nice to see the slow loop as well. And so maybe we'll do both for the interest of this, and we'll swap one out. I can talk a little bit about the similarities and what's going to happen between them. So we have the loop, and there are a number of tutorials on this online, and I'll continue to add more as I use it more. But we have the fast loop above. Like I said, we will use the fast loop in a second, but let's start with the classic loop. And we want to connect these two elements. The data that comes in will be our points. And so I'm going to even just add, so I can be precise about these, I'm going to add a point container to come out of these points. I can hide that. And so we'll start with the classic loop on the bottom. We're going to feed the points into that. The trigger is the button. And the repeat, I'm going to use, again, a panel / / as the shortcut for that. And let's set this to 10 and then enter. And so what we want to do is to take each of these points, project it down a certain amount, and then use the surface closest point to project it back to the surface, and then project it down and back up to the surface. And so the way that we'll do that is we will move these points. So we'll do a move, and the point that will move will be from that data. We can see all those points just jumped up. Let's set the unit Z. And let's add, we'll have to see what we use. I'm going to use the panel again and say -2, enter. We can change this and we'll see if it works. We may just want to refine it a little bit if it's too much. But here we can see we just moved all of these points straight down. That's good. The next thing that we'll do is we'll use this component called surface closest point. And our geometry that we have here is a point. So we'll feed this into point. We want to project this back up to the patch surface. So we'll come over to patch, pull this in, and that projects it back up, which we can see there. Then we'll take the point out, we'll feed it into the data, and now we can see it already beginning to move. So we can use our reset button. We can hide our move. We can even hide our initial point and set reset. We can see the way that those are moving now. We can even hide our start of our loop. And we can see the way that they start to be distributed on the surface based on the way that that changed. If we change the unit vector, say -1, it will move a little bit less, but we can always increase this with the number of iterations in our loop above. So let's look at one other thing, and well, a couple of things. Let's hide our surface closest point, and then using the loop, we want to record data. And we can do this for both of them. And as we do this, it will capture all of those points now. So we can see the difference that within that, as it runs the loop, what it's doing is it's creating 10 points along that length. And these are just points. If we zoom in, we can see they're just points. What we want to do is to connect those points. And so let's look at what happens if we just connect those points. We can do them with either a polyline or an interpolate curve. Polyline is probably a little less computationally intensive. And let's feed these in. We see that there's an error, insufficient points for a polyline. I like to do one other thing with this, which I like to, since I have kind of points coming in with a point container, I like to have points or a point container coming out so that I can control that a little bit. I can hide that, but I think this will still give us a problem. It still gives us that same error. So let's look at this. Just by creating a panel, let's look at what's coming out. And so what we're getting are essentially just a list of points. Let's do okay, let's do one thing. Because this is grafted all the way through this, I don't want to bring a graft into this. So back at the B-rep and curve intersection, I want to flatten this. And so by doing that, now what happens with the structure as it comes out is that we can see we end up with a list that has 24 points within it. So as we look at this, it's a little bit off. And the reason for that is that we want to flip this matrix. And so you can test these things a little bit by beginning to understand how many, so we're repeating 10 times, but we've also got 25 points as the starting point. So it's 25 and then 10 repetition. And so as we can see, we've got 0 to 24. What we can do is we can flip the matrix. What this allows us to do is think of it as changing the, say, rows versus columns in an Excel table or within an array. So as we do this, once we flip it, this will now be 11 numbers in there, which is why we have 11 numbers in our within our loop, within each one of those. So by flipping the matrix and doing this, we can hide our points. And now we see we get a series of lines along that surface. If we rerun this and reset it, now we can see the way that that moves through. We could increase our count in the loop. So let's set this to 50. And now we see that it goes through that many more times. And we get much longer trails moving across the surface. And again, remember, we could also increase the projection down. So we could go -2. And this will create even longer lines. And so it's just think that you can manage those two things. You'll have kind of less resolution by increasing this number, and you'll have more iterations by increasing the number of the counter within the loop. And so as we did that, remember the loop is running 51 times. Now our list, there'll be 51 elements in each of these. So the number of points is really increasing. Let's go back. I just want to also turn on, this was something that was a little off when I did this earlier that I didn't like. Actually, we can see our starting points where we get the intersection between our vertical lines and our patch surface. We can see that the starting point is actually one element in the loop that's being left off. And so there's a way we can work through and we can add in this extra bit of that line so that we go directly from this first point into our loop from there. So I'm going to leave that turned on for a second. So the key differences between the classic loop is that if you want an animation, in other words, as I hit reset with the button, we can see the lines being drawn. That's the classic loop. in that we see it iterating, we see it adding those points and adding as it goes. Because I want to add many more points and do and process this data in a number of ways, I actually want to swap this out, swap out the classic loop for the fast loop. And the difference is that the fast loop is just going to run and give us an output. It's not going to do it in an animated way. So going forward, just consider those two options. The classic loop is going to run a little bit slower or a lot slower for us as we do this. And so let's just, the easiest way to swap this out now is we can just set the 50 for there. We can have our points coming in. We can do that, our points coming out for the data. And then this coming out to here. So we should be able to just delete these. And now we have our loop running. We can hide the first bit, and we can see that we are recording this. So we can hide this one as well. And if we were to change anything, and we can turn this back down a little bit, maybe to 25, we just see the output. We don't see it animated. And so that's the only difference. And this is really the only thing that we're doing with the loop right there. So if you just wanted to get a sense for how this works and for the loop, you can stop the tutorial now. I'm going to keep going because I'm going to add some of those nuances related to the representation. Remember, there were a key element for where the flow line was starting. And I want to show you how to break down the flow lines and analyze the slope. And that can be a little complicated. So let's take a look at this now. So the first thing that I wanted to do is it did bug me that our loop is skipping the first bit for that. And so what I want to do is to add back in an element into our polyline, which is our first point. And the way that we can do this, and I'll just move the polyline over, knowing that we're going to do a little bit here to work with it. We can get rid of that panel. We're going to insert items into our list. And so our list will come from our flip matrix. Clean that up a little bit above. And the item that we're going to add will be these starting points. So we'll add them as the item, and the index, or indices, will be at position 0. So I'm going to use the panel //0 and plug that in to indices. So now what we end up with is a list that has that first item added to it. And now we can feed this into our polyline. And that gives us some extra lines. Let's see what we get with maybe the wrap. Okay, let's take a look at this. We don't want that to be we didn't want that flattened. Let's take a look at this with a panel. And so we have 50. Let's turn this back down. Turn that down to 10. We have that list coming in. I don't believe we need to flip the matrix again, but something seems a little bit off with that. So let's try that. That doesn't seem right either. So we have 25 of those points. Those are the points that are there. I see the problem. What we need to do is we need to graft our points. So we're going to graft tree. So these points, watch what happens if I add a panel here. This is just a straight up list. And that's what was creating a problem a second ago. But when we graft these, and I do this, now we see that they have the different index between them. And so when I include this grafted element into this list, now we have 11 elements within there. And now we have that working. So, and this is because our list coming out of the loop is grafted, and we just wanted to make sure that we added a grafted element to that list. And what we did is we added that point. If I turn it back on, we added that point at the beginning. So now as we zoom in, our polyline begins right at that point and then continues for however many iterations we want. So we can hide that point. While we're there, well, I'll turn it back on for a second just as a reference. While we're here, let's add something. If you're happy with those points and happy with the X's, I didn't like the X's because as you zoom out, you can see that their scale changes. They're a great icon as you're working with things, but in terms of representation, they're not always the best. And so the way that I wanted to do this is I wanted to add a little circle to there. And let's break down our list and just play with it for a second. So the first thing that we'll do is we'll get our, we can do this one of two ways. So let's get a sub list. So we'll go up to sets and we'll do a sub list. And so we're going to extract a subset from a list. And so the list will be our list from above. Our domain, what we want to do is we want to extract the first and second point. And so I'll do that with a panel, and I'll just say 0 to 1, enter. And so now we can see we're getting 0 and 1. And what we can do with this is we can make a small polyline using those points. So we'll use the list, we'll plug that into here. We can hide these. We can toggle this. Well, actually we can hide our polylines for a second and just keep our short polylines. This is going to give us a vector, and we can use that vector to make a plane. The reason why we need that is that I want to make a circle. So let's look at the circle component. what we need is a plane and a radius. So for the plane, that's under vector, plane. We're going to do a plane normal. So what we need is the origin and a z-axis. The z-axis is going to be our short polyline. Our origin can be our grafted list of those points. So now we see we end up with planes at the start of all of these. We'll plug our plane into our circle. Let's hide our plane. We can even hide our polyline. And now we see we get a series of circles here. Let's turn on our longer polylines. So now we see we get a circle oriented with the start of our flow line. Let's just turn the radius down, and we'll also add a custom. So for the size of the radius, I'll say 0 is less than 1.00. Adding 0.00 gives you a little bit more control. So look at what we want that to be. I also want to turn off my points from earlier. So now we have those circles. I want these circles to be custom and just a really simple thin black. So make a swatch. Just a very small notation. For the start of that. So we have those, and that's looking good. So now let's come up to our polyline. And let's just maybe play once more, look at the representation of these. If we want to go all the way back to the beginning, we can change our U and V count. So we can increase this from 5 to, let's say, 15. Now we get a larger field of these, or a more dense field. We could also increase our iterations in our loop. So let's go to 25. So now we see we also get longer lines moving across that surface. So that should look pretty good. This might also be a good time to save, because as things start to get computationally more intense, we want to make sure that things don't crash. So I'm going to save this both in Rhino and in Grasshopper. Okay, so if that looks good, I want to turn down, and we may come back and turn these down even more. I want to turn down the number of iterations and the UV count. So as we make some modifications, we really want to be able to take a look at this and control this. Okay, so the next step for us is let's look at, what I want to do is divide the curve. So I want to divide this polyline and begin to assign a different color, or before we do that, to determine the slope along at that specific length along there. I'll show you what that means now. Let's work through it. So let's start with dividing the curve. So we'll divide curve. We know that this defaults to 10, but what I would like to do is to set the count to be equal to the count of our loop. And so if we change something with the loop, granted it's 10, it's not going to look any different as we change this, but I just want to use that same loop so that as I increase the loop, this will also have an effect here. And now let's shatter this curve. And basically shattering a curve breaks a polyline into multiple segments. So we're going to shatter our polyline, and the parameters that we'll use will come from the divide curve. We can hide both of these previous components. Looks no different now, but for when we had polyline earlier, we had 25. Now with the segments, we've got 250. Remember, we've got 25 lines, and then now we have 10 divisions along that length. So let's get the endpoints, or the start and endpoints for each of these segments. We can hide the segments, and I want to, just to make this easier so I can turn them on and off, I want a point container for both the start and the end. So I can hide the points, and now I can toggle them on and off. And maybe to make this even easier, let's go back to our iterations in our loop, and let's turn this to 2. And so now with our start and end, if we look at our segments, we only have 50 of them. We have starts and we have ends. And the reason why, so the start is here, it goes to the next line, and then the next line starts, and there's a start there. And as we look at ends, again, remember, and here, let me zoom in on one of these lines. And this is where it's also helpful to have that circle at the beginning. If we look at starts, this is one segment, this is another segment. It starts here and comes to here. This segment starts here and comes to here. If we look at the ends, this segment starts here, ends here. This segment starts here and ends here. And so we get a little bit of duplication, but that should make sense for why that's the way it is. So now let's grab these. And what I want to do is to draw a line straight down, because here's what we're going to do. If you can see my mouse on the right, what I want to do is to determine this slope is that I want to look at how deep it goes. And so rise over run. And then this line will be rise over run. And so in order to do that, what I want to do is I want to draw a line from the starts straight down. So we'll use our line that we used earlier, which is line SDL. We will start at the start points. The direction will be Z. And the length, we'll use a panel again, and I'm just going to say -10. We'll see if this works. That's going to be much deeper, but at least I have a sense that that will always be deep enough to intersect the next element in the curve. And so what we want to do is to use an origin in the horizontal plane, so that's the XY origin, at the endpoints. And so I'll move these up to know that those are starts. I'll use the XY plane at the ends. And those are really large. I believe if we go up to display, we can change the size. I don't know if that changed them or not. Display, preview plane size 1. Enter. Okay. So now our planes just changed slightly. So that's a little more legible. Now what we'll do is the plane that's just an icon. It represents an infinite plane in that direction. So what we can do is to get the intersection, we use another intersection, and this time between a curve and a plane. And so we find that here, the curve plane intersection, and we'll bring these two things together. So our plane is going to be our XY plane, our curve is going to be there. Now we get the intersection between our line and this plane. And we get an intersection between our line and this plane. So let's bring these two things together and let's draw a couple of lines. So I basically want to draw a line from this point to this point and a line from this point to this point. Then I can get the length of each of those lines, and then I can compare rise over run. So let's create a line, this time now with 2 endpoints. We can copy this. We're going to need 2 of them. So the first line that we're going to make is from the start to the intersection. And for these lines, we do want to flatten this down. And now as we click on this line, we can see we get a vertical line and a vertical line. That's good. The next thing that we want is to go from the end is going to be our end point. And the start point is going to be from that intersection. We need to do the same thing. We'll flatten and flatten. And now these are the horizontal lines. So we can hide our long, tall vertical lines. We can even hide our planes. And now we can see displayed on the right-hand side, rise over run and rise over run. And so we can now get a sense for both of these, for rise over run, by capturing their lengths. Copy that once more. And now I want to divide one by the other. So this will be a division. And then I'm going to just check it with a panel and see what I'm getting. So this makes sense because if we divide it the other way, these would be much larger numbers. These are all fractions. And for whatever reason, if you mix these things up, let's do that. We can see it's 8, 1, 3, 5, 2, 6. When I did it earlier, there were some that were like 30 as well. So we want to make sure that we divide rise over run, and these should all be decimal places. So once we have that, we're really close. What we're going to do is to take these values and break them up just slightly. And so what we can do is, let's start with we want to custom color these. So we'll custom preview. The geometry that we're going to custom preview is going to be our shattered segments all the way from over here. And as we plug this into the geometry, the one thing took me a while to get this right earlier, we do want to flatten this so that it does align with our flattened list of dimensions that are there. We want to color code these using a gradient. So we'll plug that in. And the gradient that I was using earlier was from a lime green to a deep blue. Slightly desaturated and pretty dark. Okay. And you can play with these colors and do anything you need to do. So what we want to do is we want to plug in a few things here. First of all, our rise over run is going to be our parameters. We need to determine our bounds for this list of values. And we can see that our domain comes out and tells us that this is from 0.12 to 0.68. We can deconstruct a domain. And this is going to be just that simple linear deconstruct domain. And the start, we can see, is the low value. The end is the high value. We can plug both of these in for the low and the upper. Okay, so this should be working. Maybe we just want to hide a few of these other things. Some of our lines, we'll hide those intersection points. We'll hide our shattered elements as well as our points. So what we should see when we zoom out are some elements that as they get flatter, and I just might want to make our patch surface even lighter than it is. Really just ghost that in. And so now I have a better sense of these lines. So, and we're not mapping the length, we're actually mapping the slope. And so the flatter the line, it should be green. The steeper the line, it should be blue. Let's now increase some of our elements so we can take a look at this. I want to increase the loop first, because really what should be happening is along that length, we should see some variation. Because remember, this isn't just one line, this is a series of line segments. And so I'm going to increase this to 50. And now we can see that those lines are changing as they start out here on my slope. And I know that you'll have a different slope for yours. There's even this line is relatively shallow, then gets deeper, and then gets shallow again. And so you should see some of that happening with yours. If you want to manipulate your topography, I'd recommend now just simply changing the seed value that goes into your Z. You can see it gets a little funky, which is why I think later I will opt for a panel here so that I can just set a number. But check to see what's happening. And again, if we go all the way back to the right-hand side, the bounds are not fixed. These will vary based on your specific slope. So here we can see the domain, and we can even add a panel in here the domain. So we can see 0.009 relatively flat to 0.4. A different topography will yield different values, but this is a relative range of values here. And again, your black circles, you could change their size, but it gives us a sense where it starts and even what direction it's moving in. So, and I'm going to do what I said. I'm going to swap out my slider for the Z seed value. Like this might be one instance where I name this. Just because as I change it, what I didn't like was moving the slider, seeing something that I really liked, and then having it delayed and having that change. So here we can see that the slope is increasing at the edge and the water is running off the edge in that way. If you want greater slope, you could increase the flexibility of your patch surface. And if you want to see more or higher sampling, increase your U and V count. So I'm going to go from 5 to 20. That'll take a second to take effect, because remember, it's also having to go and go through the loop. But here we can see now that changing. If you want to change the size of your circles at some point, you could do that as well. As we increase the sampling, the circles now look really large. So we can make these a little bit smaller. Well, you just really want them to be a point that's there. So that's looking pretty good. And what I love about this as I zoom in is just seeing those lines change along their length based on that slope. So relatively small slope, increasing, and then decreasing again. With the gradient, you can also manipulate it slightly. So if you want to see more extreme and really clamp down on where the low values are, you could do that. Or you could move in the other direction and really just set to see where the maximum values are. We see them up here. We can set these far apart. So it's only the extreme low and the extreme high. But as we saw when we started, we can kind of move these in maybe like 25%, and you get a nice gradation that way. So change your Z values, your Z seed. We'll see the topography change. And then you'll see the flow change. Remember, you can also move this plane above. You can increase the size of that plane, decrease the size of that plane, but move this around if you want to sample a particular area within your topography. And now you also get a sense, depending on how quick your computer is, why I wanted to make that change to the fast loop compared to the classic loop, because it is a little bit slower now in order for them to run as we increase both the iterations of the loop and as we increase the sampling that's there. So the other thing that we could do is, if you wanted some representation, there was an earlier version where I had all of those points on that were here. And if we wanted to have a sense for that, we could even add just short vertical lines. Instead of -100, we could do -5 here. And just have a sense about where those vertical elements are coming from. So those are the key elements that I was excited to share. We can, let's see, we could also custom, maybe that's a smart thing to do, is to add our plane, and we can hide that plane. Oh, wrong one. But now we can have that plane above as well that just talks about your sampling area. But these were the key elements that I wanted to share with you, going from a random custom topography and generating that, which is something that we did earlier in the semester, to using that patch surface to subdividing a different surface to control another area. And again, remember, if I turn this back on, I can also scale 1D this. And so we can manipulate the surface as a sample size. So we have that level of control. We used a really simple loop to create these continuous flow lines. And then I also showed you how to take those lines, break them up, analyze the slope, and then color code that slope. So I think this produces a really beautiful representation. And then we also added those points at the start. I think it's a really beautiful representation of topography and hydrology. So if you have any questions, please drop something in the comments. Please subscribe to the channel. It's my intention to keep adding more Grasshopper tutorials and more plugins and ways to work with these things and greater workflows. So if you subscribe, I'll be more likely to continue to add things there. And check out the other tutorials. And if this was helpful, please give it a like. And I'm also open to suggestions for things too. So add something in the comments for other tutorials that you'd like to see that might be helpful for things that you're working on. Also, feel free to share what you develop with this. I'd love to see other applications for it. So hope you enjoyed this. I hope it was helpful. And watch for more tutorials coming soon. Thank you.